Hey guys, in this video we're going to be talking a little bit more about the individual states of matter. We talked about them briefly in Unit 1, but we're going to come back to them. We're also going to discuss how these are going to change from one phase to another and look at reading phase diagrams. So with all of our particles, we're dealing with the kinetic theory. So everything is made up of tiny particles that are in constant motion. So the kinetic energy is related to the energy of motion. So we're looking at the kinetic energy of individual particles. For gases, they are composed of particles. They're usually going to be molecules or atoms. All particles are considered to be small hard spheres. With gases, they tend to be a very small volume, and there tends to be a lot of empty space. So the particles are going to be far apart from one another. There are no attractive or repulsive forces between gas particles, so they're not attracted to one another. And particles in a gas are moving rapidly in constant motion. The particles in gases are going to travel in straight paths and move independently of each other. So each particle is moving whichever direction it wants to, and they'll simply kind of bounce off of each other and go in a different direction. One thing with gases, so they fill their container regardless of shape and volume. So gases are going to take both the shape and volume of whatever container they're in. And all collisions of gases are elastic, so they can exchange energy whenever they collide. And that kinetic energy is just transferred from one particle to another. The big thing that we dealt with looking at gases was gas pressure. This was the force exerted by a gas per unit surface area of an object. And the pressure is the result of how many collisions there are between those moving particles of a gas. And if you have no pressure, you have an empty space with no particles and no pressure, it's going to be inside of a vacuum. Pressure units that we dealt with in previous videos were that kilopascals, the kPa, millimeters of mercury, and atmospheres were kind of the common ones that we came across. You might be familiar with more English units of PSI or pounds per square inch, particularly when we talk about gas pressure in tires and things like that. We also have to deal with atmospheric pressure. This a lot of times can control aspects of our weather. And it's still a result of all the collisions of air molecules with objects. These are measured using barometers, and the air pressure can change with the overall weather. And overall atmospheric pressure decreases as you move away from sea level. So if you're on top of a mountain, you're going to have a lower atmospheric pressure than at sea level. With solids, so solids are kind of the other side of the spectrum where particles are so tightly packed against each other in a highly organized pattern that they are locked in place. They cannot exchange places with other particles. These tend to be very dense and incompressible because there's not a lot of empty space in there, and solids do not flow, so the particles cannot exchange with one another. Whereas with liquids, particles in liquids still have some attraction to one another. They're still touching, but the particles can exchange places. So the attractive forces between molecules are those intermolecular forces that we dealt with in our bonding unit. And the intermolecular forces allow liquids to slide past one another so the particles can exchange places. But remember, liquids have a definite volume, but they partially take the shape of their containers. So they're not going to expand to fill the container, but they will fill up to a certain volume and take that partial shape of its container. Changes of state we have to deal with a lot with our phase diagrams, and we really look at what's happening to those attractive forces between particles. So if we're going between solid and liquid, so solid to liquid is melting, the opposite, liquid to solid, is freezing. Note that these do occur at the same temperature. So for water, the melting point or freezing point is that 0 degrees Celsius. Whenever we're melting, we're weakening those intermolecular forces. So instead of the particles being locked in place, they can now exchange places and move around a little bit more. Whenever we're freezing, we're strengthening those intermolecular forces, which locks those particles in place. If we're going between liquid and gas, it's going to be boiling or vaporization if it's at the boiling point. If it's not at the boiling point, a lot of times we refer to it as evaporation. The opposite, if we're going from the gas phase into a liquid, is going to be referred to as condensation. And yet again, all of these are occurring at the same temperature. So for water, that would be the 100 degrees Celsius. And during vaporization, so going into a gas, remember gases don't have any attraction between particles. So all the intermolecular forces are being broken, while during condensation, those intermolecular forces are being formed. So that's why we're going to talk about this a little bit later, but it's going to take more energy to boil water than it would to melt water, because it's going to take more energy to break apart those intermolecular forces versus just weakening them. We're going to skip this one. The only thing I want to make note of, you don't need to worry about vapor pressure, but normal boiling point, normal melting point is the boiling point at standard pressure. So we're going to look at that when we get to our phase diagrams. Whenever boiling occurs, the vapor pressure of a substance is equal to the atmospheric pressure for boiling to occur. And as particles boil, the liquid loses particles with the most energy. So this is why if you're making mac and cheese and waiting on water to boil, you might see a couple of bubbles and then nothing happens because it lost the particles with the most energy. So it has to build up energy again to create more bubbles and have more particles go into the gas phase. Comparing boiling points, this is just going to be to a difference in that atmospheric pressure. If the atmospheric pressure is lower, liquid is going to boil at a lower temperature. So you may see if you are baking a cake or making pasta or something like that. Sometimes it will have different directions for higher elevations because everything is going to cook at a lower temperature. Other changes of state, we mentioned these back in Unit 1, but we also have sublimation deposition. So these are ones that we don't deal with too often. But sublimation is whenever a substance changes straight from a solid into the vapor phase, into a gas without becoming a liquid. So think of dry ice. If you have dry ice, you have the block of dry ice and then it immediately produces fog. It doesn't melt and then produce that fog or vapor. The same is true, you can go the opposite direction, which is deposition. This is changing from a gas to a solid without passing through that liquid phase. So it will be a gas and then it will be a crystal. So we already talked about dry ice, which is a form of carbon dioxide, does this. You can also see this in iodine. If you want to see this in action, there's a good YouTube video that there's a time lapse of where it's the sublimation of iodine. It's a teacher who puts iodine in a beaker in a fume hood, heats it up, and then has an evaporating dish with ice at the top. So you'll see the iodine turn into a purple gas, and then as soon as it hits the container with ice, you will see it recrystallize. That's a cool video to check out if you want to see sublimation and deposition in action. How we're going to be using these is reading phase diagrams. This is something that you're going to see, and it looks at what condition of temperature and pressure a substance needs to be in order to be a solid, liquid, or gas. It's also going to include where those phase changes are going to occur at certain temperatures and pressures. In phase diagrams, conditions of pressure and temperature are shown by a line separating the different phases. We're going to go over some different points that you can find on these phase diagrams, including the triple point, which is the point where all three curves meet. That's going to be able to show you the temperature and pressure that all three phases can exist together. We're also going to be able to note what's the melting point and boiling point of a substance. And we're also going to talk about the critical point. And my iPad disconnected, so I won't be able to write on it, but I'll see what I can do from this screen. So here we have the phase diagram of water. This is a very common one that we come across. Let me see if I can get a pen. There we go. And it may be a little sloppy on here, but I'll see what I can do. So here you note we have the pressure on our y-axis. You can't see it, but temperature is down here on our x-axis. It is always going to have this Y shape to a phase diagram, and it's always going to be in order from left to right. So here in purple is our solids, and the yellow in the V part is our liquid, and down here the bottom right in the blue is our gas. So you'll note where all three lines meet, this red dot is our triple point. So that's the temperature and pressure that all three phases can exist at the same time. So you might come across a question wanting to know, well, what is the triple point? So the triple point exists at a pressure of 4.58 torr and a temperature of 0.0098, and that's in degrees Celsius, but you can't see it noted down below. You can also find the normal melting point and normal boiling point, which is at standard pressure, which if you remember standard temperature and pressure on your reference sheet, standard pressure is at 1 atmosphere. So if we're looking for our melting point, which is going from solid to liquid, if you look at where that 1 atmosphere meets the line between solid and liquid, follow that down to the temperature. That's a temperature of 0 degrees Celsius would be our normal melting point at standard pressure. So I'm going to put here MP. There we go. Follow this same line across to where it meets the line between liquid and gas. So our normal boiling point, just trying to move my dot, is at 0 degrees Celsius. So that's going to be our boiling point, our BP. There we go. You can also solve problems like this, it might tell you that you're at X and you move to a pressure of Y, or you increase the pressure to Y. Well, if you just, or excuse me, increase temperature, if you go across that line from solid to liquid, the phase change that's occurring is melting. Or it might tell you that you're at point A and the pressure is increased to point B, and it wants to know what phase change occurs. Well, if you increase the pressure, it goes from being a gas into a liquid, which is condensation. So those are different ways that you're going to see questions. You might also be told you have a substance at 2 atmospheres and a temperature of 50 degrees Celsius. And wherever those meet, that would be something in the liquid phase. Let's look at another phase diagram that's pretty common you're going to see is for carbon dioxide. So carbon dioxide, this is similar, but it's going to have different values for all the different substances. So every substance will have one with the kind of Y shape, but all their values, whether it's boiling point, melting point, triple point, will be at different temperatures and pressures. So here, if you note, we have our Y shape. Our solid, liquid, gas is still the same. Our triple point where all 3 lines meet is at a pressure of 511 or 5.11 atmospheres and a temperature of negative 56.4 degrees Celsius. In terms of boiling point, melting point, so remember, normal boiling point, melting point occurred at 1 atmosphere, which is down here. If you follow that 1 atmosphere line across, it never actually reaches the line but to change into a solid. So this actually does not have a normal melting point or a normal boiling point. It can still boil or melt, but only at higher pressures, not at the normal point. So this actually has a normal sublimation point. Let's see if it'll write SP. So that's something kind of unique about carbon dioxide is that it has a sublimation point. Now, if we were at a pressure of, let's say we're at a pressure of about 50 atmospheres, we could make it melt and make it boil at that pressure, depending on what the temperature was. Another thing that you'll see on carbon dioxide is up here in the top right corner, we have our supercritical fluid. Supercritical fluid, it's where you can no longer distinguish between liquid and gas. So this is essentially going to be plasma. Let's see if I can write using the trackpad. It's a little messy. So up here you essentially have plasma. Now if you notice where the line ends between liquid and gas, that's also another feature that we can look for. That is what we call our critical point. Excuse me. It's a little more difficult writing on the trackpad. So our critical point is just the temperature and pressure where you can no longer tell the difference between the liquid phase and gas phase. So that's the temperature and pressure where you start seeing this supercritical fluid. You can still do all the same things on here that we did in the last one. So say that if we were at a pressure of 50 atmospheres and a temperature of, let's say, 0 degrees Celsius, that would be here in the liquid phase. If we increase the temperature to, let's say, 30 degrees Celsius, that would now be in the gas phase. So that would be going through boiling. You could also say if you're a gas at about 1 atmospheres and negative 60 degrees Celsius and you increase the pressure to, let's say, 10 atmospheres, that would take you from being a gas into a solid. So that would be deposition, would be the phase change that's going through. Make sure to try out the practice. It's just going to be reading a lot of these phase diagrams, being able to find those certain points on there, and looking and identifying the actual phase changes themselves.